This takes us to the conclusion of chapter 4. We're going to talk here in this slide about MATLAB commands that are relevant to manipulator inverse kinematics. So a few of these commands here I'm going to talk about in this slide, and then I'm going to show how to write them down in MATLAB command window, and then how they look like also in terms of results of these commands. So the first command here is to create link parameters, and that command is called link with a capital L. And the input to this command is you put the DH parameters, the very first row of the DH parameters, which of course is, it includes 4 elements, which is alpha, A, D, and theta. And here between 2 quotation marks, we're going to use modified convention. So this could be standard or modified. In this course, we're going to use the modified convention of defining the DH parameters. Okay, so we repeat this L. We call this, the variable for this link, we call it L1. And then we repeat this again for each link we have. If we have 3 links, then we have L1 and L2 and L3, and then so forth if we have more links or less. All right, so that's the first command that I want to talk about. The second command is how to create a robotic object. And this command is called serial link. The S here is capital and the L is capital. The input to this command is the L that we created in the previous step here, and this one. These L1 through L, however many links we have, they're all in a variable called L. So we input this L here, and then we can specify the name of the robot and have a description of that robot here. Okay, and then it's always good to call this robot a name because we're going to have to recall it later. So this robot becomes the name of the variable or the object for this particular robot that we're defining. The third command is the inverse kinematics command. So here we are using the transformation matrix to find the joint variables or the joint values for these that correspond to the transformation matrix. So the command is called ikine. The input to this is the robot that we just named earlier. So if we call this robot, then we can put this variable here, robot. And then the other input is T, transformation matrix. And then M is the mask, where the mask basically is a vector that includes 6 elements. The elements have to be either 0 or 1. So the elements are X, if we are controlling the X in the Cartesian coordinates, and then Y if we're controlling the Y, and then Z if we're controlling the Z, and then rotation about X, and rotation about Y, and rotation about Z. Okay, so if it's something that we're controlling, we can put that command as 1. If we're not controlling, we can put it as 0. Okay, so this vector would have 1s and 0s, where 1s correspond to the joint or Cartesian coordinates that we're controlling, and 0 would be corresponding to the Cartesian coordinates that we are not controlling. Okay, so here I can name this Q because it's going to give me out the joint angles corresponding to the transformation matrix. So whenever we run the ikine command, it gives me the joint angles that are needed so that my end effector will go to that pose that's defined by the transformation matrix. The for command is a command. Actually, it's not a command, it's more like a model that's already pre-specified in the Matlab-Robotics Toolbox, and it's a model of the Puma 560. Okay, so if we call this in the command line, if we put a model MDL underscore Puma 560 AKB, it already has this model, so it's going to bring out the model and have the robot already defined and already named. It's named P560M, and it will also create some initial configuration or joint angles that are defined as part of this model. Okay, so all we have to do is just type this into the command line so that we can recall this robot. The next command is a plot command. So this will plot the robot. And again, in this case, this plot is different from the plot that comes with MATLAB. This is specific to Robotics Toolbox. And inside of this, we specify the robot name, which is the same name as the name that we named it here when we defined the robot. And then Q is the configuration. How do you want the robot to look like? So Q is the joint angles that would define the configuration of the robot. Okay. Now, if we have a set of angles, just a single set of angles for the robot, then it will display these angles. But if we put here a trajectory of angles, then it will show a simulation of the robot. Okay, now I'm going to show some of these commands. I'm using here MATLAB release 2020A along with Robotics Toolbox release 10.4. So I'm going to show you some of these commands and how they look like in the command window line. In this chapter 4 here, I'm going to show an example of inverse kinematics using 3R robotic arm and also Puma robotic arm. Okay, so as we know, 3R robotic arm has two lengths. So I'm going to specify L1 and L2 as 2 and 5 units. Again, I pre-typed everything here, so I'm just going to copy and paste. So I'm going to copy this and paste it here. So that's L1 and L2. And then I'm going to write the DH parameters in a matrix form so I can use it later on as I need. So this is the DH parameters. First row corresponds to first link and joint, second row second link and joint, and third row as second link and joint. And the order for this is theta first, and then D, and then A, and then alpha. Alright, now I'm ready to create the links. So as you recall here, we use link command with a capital L, and inside here I specify the DH parameters line. So for the first link, I'm going to use the first row. So that's row 1 and columns 1 through 4. I'm going to use the modify convention that we covered in Craig's book. So this command here will specify my first link and joint. So first link is a revolute joint, that's the default. And then these are the parameters for the first link and joint combination. And then I can do the same thing to define link 2. Once I do this, it displays both link 1 and link 2. Then I can do the same thing for link 3. And it displays links 1 and 2 and 3. All of them are revolute joints, and these are the parameters for this. Now I'm ready to create my robotic object. I'm going to call it my3R, and I will use serial link with a capital S here and a capital L here. And then inside of here, I'm going to specify L as the links that I just defined here. So I'm going to input them there. And then I'll put the name for my robot as this is my first 3R arm. Okay, so I'm going to take this, copy it, and paste it here. And that will give me the DH parameters and the definition and the parameters of my arm that I called my3R. Okay, now I'm going to initially specify initial transformation matrix and desired transformation matrix for the end effector pose. So this way, if I have the initial transformation matrix for the end effector, I can use inverse kinematics to find the corresponding joint angles. Okay, so I'm going to start by defining this transformation matrix here that I already typed. So that's my initial transformation matrix. I call it TI. And then I'm going to define also my desired transformation matrix, and I called it TD, which you see right here. Alright, now I'm ready to start doing my inverse kinematics. I'd like first to define something called the mask, and this mask is needed for inverse kinematics. And with this, basically, it's a vector that corresponds to what are the Cartesian coordinates that you're controlling. So when you have a 1, that means you are controlling this Cartesian coordinate. When you have a 0, that means you are not in control of the Cartesian coordinates. And the reason we're doing this is because, as you know, the inverse kinematics needs to have a solution for your transformation matrix that you're specifying. So if you have a 3 joint system, that means you can only specify up to 3 of these Cartesian parameters to be controlled. If you have 6 degrees of freedom, you can specify 6 and so forth. So this basically tells the processor here, or this function, that what are the joint or the Cartesian parameters that we're controlling. Okay, so this is called the mask. So if we have like a Cartesian, a 3D Cartesian coordinates that would be using 6 joint robotic arm, then we can do all six of these as ones. And in this case we have only a planar robot, so we can only control the X position, the Y position, and the rotation about Z. We cannot control the Z position, and we cannot control the rotation about X or the rotation about Y. Okay, so this is how the mask matrix looks like. So this is X, Y, Z, rotation about X, rotation about Y, rotation about Z. All right, so in this case I have 3 joints, three robotic arm joints, 3 degrees of freedom, and since it's planar, I'm going to be controlling X, Y, and Z. X, Y, and rotation about Z, and that's what this mask matrix gives me. All right, now I'm ready to use the iKind command right here, and this iKind, the input to this function is the robot name, my 3R, and the transformation matrix. That would be what you would like to find the corresponding joint angles for, and then we have to specify this parameter, which is the mask, and then M is the mask that we already defined here. Okay, and this will give me Q. In this case I called it Q initial, which corresponds to the initial transformation matrix that I have. So if I take this, it will show me what are the joint angles needed to achieve I have to copy this first. I have to make sure I define M. Okay, so I defined M, and now I can run the inverse kinematics command. So this will give me Q initial that correspond to the transformation matrix T initial. Okay, so if I command my 3R robotic arm to make these 3 values for the joints in radians, what the joints are in that robot, then it will give me the transformation matrix that I put here as my T initial. Alright, I can do the same thing for the desired joint angles. So in here I have again my arm name, and I have T desired. I specified the mask, and that would give me the corresponding joint angles that would take me to T desired. So these are the angles that would take me to the desired, and these are in radians. Okay, now I'm ready to plot my robot, and I put here view 2 so that we can see it in 2D. That makes it easier. Inside the plot command I have the name of my robot and the joint angles that I would like the configuration of the arm to be plot in this example. Okay, now I plot this, and this is my initial configuration of the arm. Okay, now I can plot the same thing for the desired configuration of the arm. Copy this and paste it here, and that's my desired configuration of the arm. Okay, later on when we talk about chapter 7 about the trajectory, we're going to do simulation to go from initial to final points. Alright, now I'd like also to do the same thing using the Puma 560 robotic arm. So I'm going to clear my workspace here and my screen, start fresh. Now, as we talked about this earlier, there's already a model built in Matlab-Robotics Toolbox, and all what we need here is just to recall that model, and it has all the parameters for the Puma 560. So that model is called MDL underscore Puma 560 AKB. So if I copy this and paste it here, it recalls that model, and as you can see here, it automatically generated the robot, which is named P560M, and Q ready, which are the joint angles when the arm is at the ready position, Q stretch, which are the joint angles when the arm is at a fully stretched position, and QZ, which is when all the joints are zeros. Okay, so now if I would like to see how this looks like, I can just type the name of the arm, P560, that's already defined, and that would show me the arm here, Puma 560, 6 axes, RRRR, and these are the DH parameters for the arm. Okay, I can also see what QZ looks like when all the joints are zeros. As you can hear, all 6 joints are zeros. And I can see what QR looks like here. Here when the arm is at the ready position. Okay, and then I can see how they look like also when the arm is fully stretched. These are the 6 joint angles when the arm is fully stretched. Okay, now we are ready to go ahead and find the initial Cartesian pose. And for this we're going to use again inverse kinematics. So I defined here initial transformation matrix and desired transformation matrix. So this here corresponds to where I would like my end effector to be in the initial stage. So I'm going to copy this and paste it here. So this is my initial transformation matrix. And then I'm going to also copy my desired transformation matrix and paste it right here. So that's T initial and T desired. And both of these, and for this example, are given. And now I'm ready to define my mask. Remember when we did the 3R, the mask was we were only able to control X, Y, and rotation about Z because we had only 3 joints. Here we have 6 joints, so we can control X, Y, Z, and rotation about X, rotation about Y, rotation about Z. Okay, so that mask gives me the freedom to control all 6 axes at the end effector. So now I'm ready to do the inverse kinematics using the I-kind. The input to this function is the name of the arm, P560M, and the transformation matrix where I would like to do the inverse kinematics for, so that I can find the corresponding joint angles. And then I'm going to define the mask right here. Okay, so this, if I copy this and paste it here, oh, again, I did not copy the mask. Let me copy the mask, paste it here first. And now after copying the mask, I'm going to do the inverse kinematics because I used M here, so I have to define it first. Now, here you can see when I put this here, I got the joint values that correspond to my initial transformation matrix. So these are the values of the joints that I need to specify so that my end effector, would go to this particular transformation matrix. Okay, I can do the same thing for the desired transformation matrix and find the corresponding desired joint angles. So this is Q desired, and these are the 6 angles that are needed to go to T desired. Now I can plot both of these to show you how they look like. Again, in the plot command, I'm specifying the name of the arm, P560M, and I'm specifying the joint angles that will give me the configuration of the arm as I need to plot it. So, and here I used view 80 and 60, so that gives me the azimuth and elevation of the viewpoint. So I can see the arm from a point that would make it a little clear. So if I go ahead and put this command here, I can see my Puma 560 arm, 6 joints. This is joint 1, 2, and 3, and then 4, 5, and 6 are here and the rest. Okay, so this is my initial configuration, and then I can do the same thing for my desired configuration. Copy this and paste it here, and that would be how the robotic arm would look like for my desired configuration. All right. And that takes us to the end of our chapter 4, inverse kinematics. We covered some theory, we covered some examples, and here we covered also some MATLAB commands, and we saw how we can implement these MATLAB commands in MATLAB environment. Thank you.